Okay, now let's talk about power. We define power to be a change in energy of our system divided by a change in time. Okay, so this is basically saying, work is the amount, what happens to change energy of a system. Power is basically how fast is that happening. So I could push on a box and make it speed up, but I could just push with a small force and go over a long distance, and it speeds up over a long time. So the power would be small. Or I could push on that box and push really hard, and that would speed up really fast, and so time is small, and so I'd get a large power, even if the final speeds are the same speeds. So the change of kinetic energy is the same. So power is just simply what is the rate at which you're doing work on the system. Okay? So with that, let's go ahead and see there's a really useful way of describing power. So this is the most fundamental. We mostly apply it by thinking about the work done on a system. And here I'm using a little dW to emphasize this is a derivative, so in case the work is changing over time. But this, remember, this is just simply a little amount of work to cause this little change in energy. I could rewrite this and say this is dE system over dt if the change is at a constant rate equals just work over dt, because work is defined as a change in the system, energy of the system. Okay, but thinking again of this little d as being a small amount of work done, okay, I can write that and say, okay, well, work is this little bit of work, it would be equal to a force dotted with a little bit of displacement. Okay, because work is force times distance, only with the full vector form is the dot product. Okay, and then divided by the dt. Right now, what's interesting here is that if the force is constant, then well, I guess I could speak even more generally. In this moment, we're looking at really small displacements. This d is just a really small amount of time. And so I can just take that as a fraction and do f dot ds over dt. And what is that? Okay, that is velocity. So we have f dotted with velocity. And this is a really cool way of looking at power. It is the force you're using times how fast the object's going. And so the product of the two, particularly the dot product, gives you that power. Now remember that that is just a convenient functional way of looking at it when the definition is given by the amount of work done in time. Okay, so this is often the more functional way. Sorry, I could put a delta here. This is the more functional way of doing it. And then this is a convenient form. Now I just want to remind about this dot product and those vectors. What it means is you take the magnitude of the force times the magnitude of velocity times the cosine of the angle between them. And that allows you to have negatives for if the force is pushing on it, but the velocity is going the other way. For example, a fridge rolling down a ramp and I'm pushing against the fridge, that would be a negative power. I'd be doing a negative power on it.